Hello ladies and gentlemen, so this last video of chapter 17 will deal with solubility products and complex ion formations. However, if you've made it through the last video, this will be significantly easier than, say, what we've just gone through. So, we're starting with KSPs, or salt precipitations. The idea is some salts are insoluble. Silver chloride, magnesium hydroxide, iron carbonate. There's a lot of them. We learned them. Here's some rules, or here's a table of what precipitates and what doesn't. But there is an equilibria expression behind it, and there's some complicated inorganic chemistry behind that of why this is soluble and this is not. But largely speaking, it comes down to K values. So the idea here is that the solubility is determined by the Ksp, this expression that says how much salt could possibly dissolve into solution. And the idea is that in insoluble salts, the Ksp is incredibly small, meaning only trace concentrations are allowed to dissolve. And so anytime we have any quantities of cation and anion together, they will rapidly crystallize as a precipitate, so long as both are present. Now, for a given equation, the K expression we're looking at is silver chloride dissolving into silver plus and chloride minus. Solubility, remember, only depends on aqueous and gaseous components. So the set amount of silver chloride that will dissolve is set in stone regardless of the amount of solid. It doesn't matter if we have trace amounts or a ton, only so much can possibly dissolve, because we essentially reach a saturated solution rapidly. The only way to really increase the solubility is one of three ways. One, increasing the temperature, which will change the equilibrium constant K. So if this is endothermic, raising the temperature will increase the solubility. We can increase the volume, thus lowering the relative molarities of the dissolved salts. And so if 1 gram dissolves per liter and you upped it to 2 liters, then 2 grams can dissolve. Essentially, it drops the Q gets smaller, and so it has to go towards more products to get back to K. Or by removing one of the ions through Le Chatelier's principle. If you can react the silver or the chloride into some other compound, then we have removed a product, and so more can dissolve. But since the Ksp only depends on solid, aqueous and not solids, it's just going to be Ksp is equal to silver concentration times chloride concentration. And so with a Ksp of 1.8 times 10 to the negative 10th, this means that only 1.3 times 10 to the negative 5th molar of silver chloride could possibly dissolve, which essentially is about 2 milligrams per liter. And if you have anything more than 2 milligrams in solution, you won't really be able to notice that 2 milligrams dissolving. But how do we calculate Ksp? Well, once again, we can use ice. However, there's a neat little thing about this. Because silver chloride is a solid, it is ignored. And so we just say, well, if 0 silver and silver chloride are present, then the concentration is just x and x, and it becomes x squared. And so if we square root that, square root both sides, we can find what is the concentration of silver or chloride that will dissolve. However, things get a little bit trickier if you have things that have different coefficients. So lead chloride, when lead chloride dissolves, the Ksp is lead 2 plus times chloride squared. But when we write the ice table, for every 1 lead chloride that dissolves, we get 1 lead and 2 chlorides. And so it becomes x and 2x respectively. So x times 2x squared becomes 4x squared times x, which is 4x cubed. So we have to solve Ksp by dividing it by 4 and then cube rooting to get the concentration for lead. And remembering that chloride is still double that. So 1.6 times 10 to the negative second and 3.2 times 10 to the negative second would dissolve. Not a ton, but some would. But with that in mind, we can do that. Barium sulfate. How much barium sulfate would dissolve if this is the Ksp at room temperature? So Ksp is 108 times 10 to the negative 10th. We have BaSO4. With that in mind, let's solve this. Let's solve this. BaSO4 dissolves into Ba 2 plus and SO4 2 minus. Don't get break happy, it's just going to cleave right down the middle. So there's going to be X and this is going to be X. So Ksp is going to be equal to X squared. So square root both sides. So 108 times 10 to the negative 10th. We square root that, and that's going to be the X, our concentration. We can do that. Square root of 108 times 10 negative 10, which it's a really small number. It's something like we'll say 104 times 10 to the negative 5th. Square root of the 10th. Move that down. So really small concentration. Some does dissolve, but not a whole lot. Not a whole lot at all. But as I said, significantly easier than any titration expression we just ran. Now this one is a little bit harder. Well, actually, this is much harder. Lanthanum trifluoride, or lanthanum 3-fluoride, if the Ksp is 2 times 10 to the negative 19th. The hint I give you is lanthanum trifluoride. It's going to split into lanthanum 3 plus and 3F minus. So let's look at this. So the first thing to remember is that Ksp is going to be equal to lanthanum 3 plus fluoride cubed. And this is 0, 0 plus x plus 3x. So it becomes x times 3x cubed. So 3 times 3 times 3 is 27. So 27x to the 4th is equal to our Ksp of 2 times 10 to the negative 19th. Solving for that, step 1. Divide that by 27. That gets x to the 4th. An easy way to do a 4th root is just 2 square roots. And that'll give you the concentration of lanthanum 2 plus. So 2 times 10 root negative 19 divide that by 27. And then let's square root out my answer, and I get the concentration is a mere 9.28 times 10 to the 10 to the negative 6th molar, and F minus is just going to be 3 times that. So that's going to be 2.78 times 10 to the negative 5th molar. But it's doable. It's doable. That one is one of the more challenging ones, but it's doable. I rounded those, but yeah, it's good enough. Now, the common ion effect, how that affects it. The common ion effect has some of the same effects with Ksp as it did with weak acids. So, for example, if there's a lot of the common salt ion, like chloride in solution, this will drastically decrease the amount of silver that can possibly dissolve. So if you add some extra chloride in there, a lot less silver is going to dissolve. The same can be said by any basic insoluble salts like magnesium hydroxide. Under highly basic conditions, they are much less soluble than they would be in neutral conditions. But on the counterpoint, they are highly soluble in acidic conditions because they start to react and dissolve. We neutralize the base, and thus we remove the base, and so more magnesium hydroxide starts to dissolve in order to replace the base that is being neutralized. Now, our last slide here is about complex ions. This complex ions are unique situations where metals are hydrated by various things called ligands. These are essentially Lewis bases that are binding to the metals and help stabilize them. Whenever a metal is floating around in water, it is being hydrated by these various ligands. So, like nickel hexaaqua has 6 water ligands. Iron thiocyanate, well, it has some understood water ligands. The big thing is the fact that we binding iron, the thiocyanate. Silver cyanide is another such complex ion. Some of these can be charged, some of these can be neutral, but the fact is they're aqueous and not solid. They are charged or neutral species that are aqueous in water. And so they have their own K expressions for these reactions. These complex formations can lead to increased solubility in insoluble salts, such that when an ion is complexed, it is bound and it acts differently than a free ion. So if I add cyanide into solution, more silver chloride would dissolve because silver would become complexed with the cyanide. That iron would normally be insoluble in carbonate, but if I add some thiocyanate, iron could potentially be soluble, or at least more soluble because the iron is being complexed. So the idea is that these guys are different from just free ions and should be treated differently, thusly. But that is where we will stop this chapter. Next chapter, we will move on to thermodynamics, where we'll look at enthalpy and entropy. We'll look at enthalpy again, but we'll add in entropy and Gibbs free energy, among other things. Until then, have a good evening.